This week we're talking about simple machines. What exactly makes a machine a simple machine? Well, a machine is any device that makes work easier. We learned in the last chapter that work means using a force to move something a distance. A machine can change the size, the direction, or the distance over which a force acts. So that means a machine can allow you to use less force, a machine can allow you to move an object a greater distance, or a machine can allow you to change the direction of the force that you're using, which in essence makes work much easier. There are two forces involved. The first force is called the input force. When we write this in an equation, we call it F for force, I for input, so Fi. And this is the force applied by you to the machine. There's always two parts. You have to apply a force, and then the machine applies another force. The other type of force is called the output force, also known as the Fo. This is the force applied by the machine to whatever object you're trying to move. Since there are two forces, there are also two types of work being done. The first, of course, is input work. This is the work done to a machine. This is the work that you would be doing if you were using a machine. It's equal to the input force times the distance through which that force acts. So in other words, it's saying it's equal to how much force you apply times the distance that you move in order to move the machine. The other type of work is output work. Output work is the work done by a machine. That's equal to the output force times the distance through which the resistance moves, or the force that the machine applies times the distance that the machine moves the object. What do you think? Can you get more work out than you put in? If you are using a machine and you put in a certain amount of force to move the machine a certain distance, and then the machine kind of transfers that work into the force it applies to the object and the distance it moves the object, can you ever do less work than the machine? The answer is output work, or the work the machine does, can never be greater than input work. So even though machines make work easier, they're still not multiplying the amount of work you can do. You still have to do more work than the machine. Why is this? Because some work is always needed to overcome the friction between the machine and the object it's moving, or the friction in the machine itself, or the friction between you and the machine. There are ways to measure how good a machine is. That is called mechanical advantage. It means the number of times the machine multiplies your input force. So it means how much greater is the force of the machine compared to the force that you put in. This is kind of an ideal mathematical thing, so it doesn't have any units. The units end up canceling each other out. The general equation is mechanical advantage equals output force, which is what the machine does, divided by input force, which is what you do. There are two types of mechanical advantage. There's ideal mechanical advantage and actual mechanical advantage. Ideal mechanical advantage means that for this particular problem, we're going to pretend that there's no friction. We're going to ignore friction. It's calculated differently for different machines. So if you use a wheel and axle or a lever or a pulley, you calculate the mechanical advantage differently for each of those machines. Usually, though, it's some form of input distance divided by output distance. Actual mechanical advantage, however, does involve friction, and it's calculated the same for all machines no matter what. We're going to focus on ideal mechanical advantage because it's a little bit less complicated. There are different mechanical advantages. You can have a mechanical advantage that's equal to 1, and that means the output force from the machine is equal to the input force from you. This type of machine would change the direction of the force that you apply. It wouldn't change the distance or the amount of force. Think of something like a seesaw. The force on one side of the seesaw has to be the same as the force on the other side of the seesaw to get it to go up and down, but the direction of the force gets changed. Then there's a mechanical advantage of less than 1. This is an increase in the distance an object's moved with the same force. Think of like using a rake. You can pick up a bunch of leaves with the rake, or you can use the rake to pull the leaves or push the leaves somewhere, and you're going to use the same amount of force to move those leaves. However, the rake allows you to use that force over a longer distance, so it makes it a little more efficient. Let's talk about efficiency. Efficiency can never be greater than 100%. Any idea why? It's because some work is always needed to overcome friction. Some work that either you or the machine does, or both, always has to overcome the friction that's in the system. Efficiency is a percentage comparison of input work to output work. And it's calculated output work, or WO, divided by input work, or WI. So we've talked about mechanical advantage, we've talked about the general definition of a machine. Now let's focus on the specific 6 simple machines and how you would calculate the mechanical advantage for each. First one we're going to talk about is the lever. This is a bar that's free to pivot or move about a fixed point when an input force is applied. That fixed point is called the fulcrum. This is the pivot point of the lever. It's kind of where the lever rocks or turns. There are 3 classes of levers based on the positioning of effort force, resistance force, and fulcrum, or input force, output force, and the fulcrum. First class levers have the fulcrum in the middle. They have the fulcrum located between the effort and the resistance. So some examples here. Here's an example of where the fulcrum is on both of these. And then the effort force and the resistance force would be on either side. So here and here compared to here and here. First class levers make work easier by multiplying the effort force and changing the direction of that force. Second class levers have the resistance in the middle. The resistance is the same as the output force. This is between the fulcrum and the effort force, or the input force, like a door. The resistance is here in the middle of the door. The fulcrum would be the hinges that it's hinging on, and the effort would be where you apply the force at the doorknob. Second class levers make work easier by multiplying the effort force, but not changing the direction. Third class levers have the effort force between the resistance and the fulcrum. So these are the least efficient. They don't multiply the effort force, they only multiply the distance. So if you think of using a shovel, here's the work, here's the object you're trying to move. So this is where the resistance force or the output force would be. The fulcrum would be back here at this hand. The fulcrum would be back here at this hand, and you have to pick up the shovel with this middle hand. For the mechanical advantage of levers, again we're calculating ideal mechanical advantage. You use the formula input arm length divided by output arm length. Let's talk about what those are. The input arm is the distance from the input force, which is where you apply a force, to the fulcrum. So it would be this length here. The output arm is equal to the distance from the output force to the fulcrum. So the output force is where the machine does its force, like on the nail, and the fulcrum is the pivot point, which is here in the middle. So The red section is the input arm and the blue section is the output arm. To find the mechanical advantage of that crowbar, you would do input arm divided by output arm. Now let's talk about the wheel and axle. This is a lever that rotates in a circle. It's a combination of two different wheels of different sizes. The smaller wheel is termed the axle, and its mechanical advantage is calculated by the radius of the wheel divided by the radius of the axle. Let's just go over, just so you remember, the radius means from the center point to the outside edge, so that would be the radius. Here's the radius of this wheel, and here's the radius of this wheel. The axle would be that center point, so you would have to calculate, or you would have to measure two radiuses. Now how about the inclined plane? An inclined plane is a slanted surface that's used to raise or lower an object. For example, ramps, stairs, and ladders are all inclined planes. To calculate the mechanical advantage of an inclined plane, you take the length of the ramp divided by the height of the ramp. This is a fairly easy calculation. The mechanical advantage of an inclined plane can never be less than 1. Moving on to our fourth machine, we are talking about the wedge. Here are some examples. The wedge is like an inclined plane because it has that triangular shape, but it moves. For example, a knife, an axe, or a razor blade, these are all wedges. The mechanical advantage of the wedge is increased when you sharpen the wedge. When you make that sharp edge sharper, you increase its mechanical advantage. And you do not have to worry about calculating the mechanical advantage of a wedge. The fifth machine is the screw. This is another inclined plane, but this time the inclined plane is wrapped around a cylinder. The closer the threads of the screw, the greater its mechanical advantage. Here's some examples of things you've seen. So as you take the inclined plane and you wrap it around, it forms this spiral shape. Even a spiral staircase is a screw. And the final type of simple machine that we're discussing is the pulley. This is a chain, belt, or rope that's wrapped around a wheel. The pulley is great because it can either change the direction or the amount of force, and if you put more than one pulley together, it can change both. You find pulleys in places like on flags and to raise the blinds in at a window or for a stage curtain. There's more than one type of pulley, just like there's more than one type of lever. The mechanical advantage of the pulley equals the number of ropes that apply an upward force. There's a fixed pulley. The fixed pulley can only change the direction of a force, and that will have a mechanical advantage of 1. And then there's a movable pulley. A movable pulley can multiply an effort force, meaning your force, but can't change the direction. So that means if you're using a movable pulley, the pulley is attached to the object you're moving, and if you pull up, the object would also go up. Or if you pull down, the object would also go down. This type of pulley has a mechanical advantage of greater than 1. Now, if you take more than one simple machine and you put it together, you actually get a compound machine. Sometimes some things that we think of as simple machines are actually compound machines. You still cannot get more work out of a compound machine than you put in. So examples, a mixer or a crane or even a pencil sharpener, which seems fairly simple, but a pencil sharpener includes wheel and axle, lever, and wedge on the inside. That's all you need to know about simple machines. If you have any questions, make sure you send me a message.